Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is secondary stresses. Till now, what we understand, what are the various types of structures, what are based on their type, based on their geometric properties, based on their material, what we used. So these are all we consider. So according to that, we are going to understand what type of arch is required for what type of arches are helpful for construction of various structures like bridges, so long span bridges. So at that particular time, so we are going to identify various types of properties. We are finding the normal thrust, horizontal thrust, radial shear stresses like that. Those are all comes under primary stresses. So in this arches, secondary stresses are also involved. They are also play a role for understanding the arches and for understanding the scenarios and situations where we are going to build those kind of structure. So in a particular structure, we are using these arches as elements. So in those conditions, we are calculated those thrust, radial shears, and which type of shape is helpful, whether it is parabolic, semicircular arch. These are all we understand in stresses. So coming to these secondary stresses in arch. So this because based on the temperature changes and elastic shortening or contraction of the arch rib. So according to these heating, so in some of the scenarios, the uniform heating we are going to analyze and the differential heating. So in generally most of the practical considerations we are observing differential temperature changes. The temperature changes are very dynamically, they are going to change in any scenario. So from winter to when we are consider these temperatures changes in so many ways, in such like that seasonal variations. So winter, summer, like that rainy seasons. So like that we are going to consider. Otherwise, day, morning and evening, day, night. So like that also the temperatures are going to changes. So how the arch which is one of the element in the structure, how it helpful for understanding these temperature effects. So we will see in this lecture. So in this majorly secondary stresses in two hinged arches can occur due to temperature changes and also the elastic shortening. So in this temperature changes on two hinged arches, when a structure experience temperature changes means expansion, contraction occurs. So whenever these two hinged arches cannot freely expand or contract at their hinges, this restraint so induce these secondary stresses. Because of this, length of the arch, once we speak, this is the length of the arch. And we are fixed the starting point and ending hinges. These hinges, we are fixed. This is the starting point and ending point here. This is symmetrical in unsymmetrical also the same scenario. But we are, they cannot freely expand. They cannot freely expand. So because of these restriction induces leads to these secondary stresses in arches. Because of the temperature stresses, because we know the span between the starting and ending point of the arch. This is the span of the arch. So we are going to restrict the expansions at end points of the arch. So whether it is symmetric or unsymmetric condition, so we are restrict. So because of this restriction, we are getting these secondary it leads to these secondary stresses. So here, how we derive these various conditions. So the change in length due to this temperature, that is nothing but the change in length. This is nothing but the change in length. This alpha is nothing but the coefficient of thermal expansion. So delta L is equal to alpha, and L is nothing but the original length of the arch. So we know this original length of the arch is L, and delta T is the temperature, change in temperature. So this delta L is equal to alpha L delta T. We understand this length change due to temperature using this formula. So for two-hinged arch, this expansion is resisted, producing a horizontal thrust. So to balance the structural restraint. So based on that, this horizontal thrust is equal to E into A alpha delta T and L into elasticity factors. So like this, we are understanding here E is nothing but the modulus of elasticity. It depends upon the which type of material is there for at the time of construction of the arch element. So what type of element, what type of material it is there at the, so that is the elastic constant. It influences the change in the for getting this horizontal thrust. So for getting this horizontal thrust, we are understanding like this. This is the formula we are using for these conditions. In differential temperature, so whenever occurs when the top and bottom of the arch rib experiences different temperature, for example, sun on one side and shade on the other. So within the this maybe it is affected by sun. So it is for the only for shadow. So these scenarios we may observe within the length of this arch. So such type of temperatural difference, temperature, how we are understanding what are their effects and what is the result for this. It induced bending movements in the arch due to the uneven expansions. Because of the uneven expansions throughout the length, there is no similarity between the effect of the temperature. So it induced bending movement in the arch due to the uneven expansion of the top and bottom fibers of the E of that particular ribs, that particular arch ribs. So whenever we are considered, so throughout the length of the arch, which it has maybe uniform temperature changes. So what is the scenario we will see in the previous slide. Now here the differential. So half of the, for example, so half of the, not only half, some portion of the length of the arch belongs to the temperature effects is different, the remaining is different. It depends upon the where the place of the arch, and that affects the bending moment in the arch due to the uneven expansions of the top and bottom fibers of the arch. So this results curvature change and additional bending stresses. So these are we are going to understand in this differential temperature. At the time of differential temperature, we have to understand these kind of scenarios. So here, so the bending moment. So whenever we understand for the uniformity it is there, for that particular condition, we have this normal thrust. Here, the bending moment due to the differential temperature is equal to temperature difference by R. Here, R is nothing but the radius of the curvature of the arch rib. I is nothing but the moment of inertia. E is a similar elastic constant. What type of material we are choose and what type of material is existing for the at the time of construction of the arch. So the temperature difference between the top and bottom fibers. So in this, so these are the temperature effects. So whenever we are comes under these secondary changes, those temperature changes uniform or differential heating of the particular arch. So these are the effects we will get for these temperature changes. Now elastic shortening of the arch rib. So it refers the reduction in length of the arch rib under compressive forces. So the shortening affects the geometry of the arch and creates additional secondary stresses because of the electric shortening of the arch of the ridge. So it reduces the length of the arch, and because of these compressive forces, so it affects the geometry of the arch and it creates additional secondary stresses. So under applied loads, the arch rib experiences the compression, causing a shortening in its length, which in turn alters the arch horizontal thrust. It affects the, so now the change in geometry. So the shortening in the rib can lead to an increase in horizontal thrust to maintain equilibrium. So the change in geometry is required to, because it is because the shortening of the rib, it is going to lead, it increases the horizontal thrust to maintain the equilibrium. So in this, the secondary stresses, whenever we are, whatever the horizontal thrust and altered geometry create additional stresses, because in this ridge we are considered as secondary stresses. So here, because of the shortening length, so delta S is the shortening length, that axial force, length and electric constants and the area. So this shortening lets this horizontal thrust is nothing but the P by L. So this total secondary stress due to the elastic shortening is proportional to change in thrust. Coming to this total secondary stress, so the combined secondary stress due to temperature effects and elastic shortening can obtain by superposing the horizontal thrust and movement effects due to each phenomenon. So this combined stresses due to, because of the temperature effects and elastic shortening, so they are going to affect these movements as well as the horizontal thrust. Horizontal thrust and movements effects due to each phenomenon. For example, so whenever a two-hinged arch has a span of 40 meters, it is the span of 40 meters, and radius, this curvature, this radius is equal to 20 meters. A uniform temperature, here we understand the complete, it is a uniform temperature, and the modulus of velocity is equal to 200 gigapascals. The cross-sectional area also mentioned, that is equal to 0.3 meter square, and the coefficient of thermal expansion is equal to 12 into 10 to the power of minus 6 centigrade. So this is the thermal expansion form. These are the given data. Now we are going to identify the problem is a two-hinged, it is a two-hinged circular arch. Now calculate the change in the length of the arch due to the temperature increase, because of the temperature increase. So we know the formula, according to the formula, delta L is equal to alpha L delta T. So finally we will get this change is 0.0. After done all the calculation, we will get this in meters. So the change in length. So determine the horizontal thrust due to this temperature, and we are going to substitute the values what we are getting from these, and based on the given data, this is the horizontal thrust value. Like this we are understanding the problem based on the uniformity, uniform temperature changes is there in this particular condition. Now whenever a parabolic arch, so a parabolic arch with a span of, here it is a span of 50 meters, and the rise from here to here at the midpoint, the rise, so here it is equal to 25, it is here it is equal to 25, overall that is equal to 50 meters. So the rise is equal to 8 meters, and the top of the arch is 20 degrees, hotter than the bottom. So here it is a differential temperature. It means it is a differential temperature changes within the arch, for the arch. So that changes top of the arch is 20 degrees C and it is hotter than the bottom. So calculate the bending moment and also the secondary stresses for elastic constant E is equal to 200 GPa and moment of inertia is equal to 0.25 m the power of 4. R is equal to 25 meters. We know the based on using this formula, substitute all the values. So the temperature difference is 20 degrees. The temperature difference here, this is nothing but the 20 degrees. Remaining, this is the moment of inertia 0.25 and elastic constant. So this is the value. Therefore, the bending moment induced due to the differential temperature is equal to 40 kilonewton meter as per the given data. Now, one more condition we are going to understand, that is a two-hinged arch. Here the arch is and the length of the arch is equal to 40 meters and it is subjected to an axial load 500 kilonewton and the cross-sectional area. So here they give this load is equal to 500 kilonewton, that is the axial load, and its cross-sectional area is equal to given, velocity is equal to given, velocity constant is given. Calculate the elastic shortening and the induced horizontal thrust. So it is a two-hinged arch. So now calculate the elastic shortening, that is nothing but the delta LS by PL by EA. That gives substitute values, we will get this change in length, the shortening, how much it is shortening, that is equal to 0.00033 meters in terms of meters. This much shortening is happen as per the given numerical values. Now substitute all the values. Now find out the horizontal thrust due to elastic shortening, that is HS is equal to P by L is equal to 500 by 40. So this is the horizontal thrust due to elastic shortening. So like this we are understanding at the time of uniform temperature and differential temperature conditions and elastic shortening. In this, movement is going to change and also the horizontal thrust. These are the stresses which we are going to understand in this particular concept. So now combined effect of the temperature and elastic shortening. So here the total secondary stresses in two-hinged arch due to both temperature changes and elastic shortening, it is going to superposition of the stresses induced by the each phenomena. So H total, horizontal thrust total due to horizontal thrust for the temperature, whether it is belongs to uniform or differential, whether it is belongs to horizontal, uniform, this horizontal thrust, whether it is belongs to uniform or differential conditions. Now this HS is the for the shortening, elastic shortening horizontal thrust. Now this moment total is equal to MT plus MS. This MT is nothing but the temperature changes as well as the elastic shortening respectively. So this combined gives the total horizontal secondary stresses and comes under secondary stresses. Those are horizontal thrust and movement. Movements which we are considered for the both temperature and elastic shortening. Now, consider one of the problem. Whenever we are consider a two-hinged steel arch, here they mentioned the type of material. So, because based on the material, type of material, the elastic E is dependent. So, here that is it is a two-hinged steel arch and with a span of 30 meters and a rise at height. So, it means from here to here. So, 15 meters and 15 meters. So, the rise it is nothing but the H is equal to 6 meters. And the area of cross section, the total area of cross section is given 0.25. Experience it is considered under uniform temperature changes. Here, the complete element, this arch, this steel arch is going to change its length or whatever the secondary stresses are getting based on the uniform temperature. So, throughout the length of the span, it affects this. It's under the same temperature conditions. So, that is the change of temperature. That is nothing but the delta T is equal to 50 degrees C. Here, the total under an axial load of 400 kilonewton. Under the axial load of 400 kilonewton. Now, calculate the total secondary stresses due to this temperature and elastic shortening. So, the total temperature stresses first, from these, the total temperature stresses total that is equal to HT plus HS. So, this is from the horizontal thrust from temperature. Here the condition is uniform temperature and also the horizontal thrust from secondary elastic shortening movements. So, here the secondary stresses are horizontal thrust, as well as movements. These are there. These are the stresses. So, total is equal to MT, horizontal thrust from temperature, and secondary stresses from elastic shortening movements. So, this is the total. This we are going to find out for the moment of inertia 0.3. And also, he also mentioned expansion also given. This is the given data. These are the things we are going to find out. These are the secondary stresses. So, now this is the given data. The overall length of the span of the arch, rise, cross-sectional area, uniform temperature change, axial load, coefficient of expansion, modulus of velocity, moment of inertia. These are the things they are mentioned. So, now calculate each and every step. After that, combine those values that gives the total horizontal thrust, and that is nothing but the secondary stress which is coming from the effect of the temperature as well as the elastic shortening. So, now this elongation of the arch due to temperature, this formula is equal to delta L is equal to alpha L delta T. Substitute the values, and this represents the expansion of the arch due to temperature change. Now, calculate the horizontal thrust generated due to this temperature change. That formula is equal to L. So, substitute all the known values into it. We will get the horizontal thrust due to uniform temperature increase. So, this is the value. Now, we find out now from temperature we completed the horizontal thrust. Now, move on to the calculate the elastic shortening and corresponding horizontal thrust. So, this is the formula for elastic shortening for the horizontal thrust. So, substitute all the values, we will get the elastic shortening of the arch due to the axial load. So, using this formula, we substitute all the values, we will get the elastic shortening of the arch due to the axial load. Now the horizontal thrust for this elastic shortening, we know the formula. According to formula, substitute the values, we will get the horizontal thrust due to elastic shortening. So after getting this, find out the addition of this, we will give the total horizontal thrust. That is the one of the secondary stress which is coming from the both conditions, that is based on the temperature effects as well as the elastic shortening. Now another problem. So here it is also a two-hinged arch and also it is subjected to differential temperature change. The previous one, it is a uniform temperature changes. Here it is the differential temperature changes. Differential temperature changes where the top fiber is 15 degrees C, 15 degrees hotter than the bottom fiber. So the cross sectional area is equal to 0.4 meter square and the moment of inertia is given, modulus of velocity is mentioned, and also known thing is the coefficient of thermal expansion. So find the bending moment and horizontal thrust generated due to this differential temperature. First find out the movement of the differential temperature using the form. Based on the formula, we are going to find out, these are the given data which is there. Substitute all the values, we will get the bending moment induced due to the differential temperature. Now calculate the horizontal thrust due to the differential temperature. Based on the formula, we are going to find out the horizontal thrust generated due to this differential temperature. So now another problem. Understand this, a parabolic arch which has the length of the span is 60 meters and rise is nothing but the 10 meters rise of the arch, subjected to axial load is 600 kilonewton and uniform temperature decrease it is there. So that is delta T is equal to 20 degrees C, it is decreases. The cross sectional area of arch is 0.5 meter square. The moment of inertia is mentioned, the velocity, modulus of velocity is there, expansion of the thermal expansion is the known thing. So calculate the total secondary horizontal thrust and bending moment in the arch due to both temperature change and elastic shortening. The step 1, first find out the horizontal thrust and horizontal thrust due to temperature changes. Find out the horizontal thrust from elastic shortening and add those two. That gives the total horizontal thrust from this condition. Similarly, find out the bending moment. So in this step 1, find out the bending moment due to the temperature effect and find out the bending moment with respect to the elastic shortening. That combination gives the total bending moment from both the conditions. So like this we are finding the problem. So the first, find out the horizontal thrust due to temperature change. The first step, find out the temperature change, whether it is belongs to uniform or whether it is belongs to differential. Using the respective formula, we are finding this. Here it is decrease, that's why we use this negative minus. So that that negative, the minus, this sign indicates the compression. It indicates the compression. Now elastic shortening and horizontal thrust due to the axial load. So find out the elastic shortening, substitute the values. Finally, we will get the horizontal thrust due to this elastic shortening condition. Similarly, total thrust. So once we find out in both the scenarios, we are going to find out the horizontal thrust. This negative sign indicates the compression. Similarly, the bending moment due to the temperature. So the bending moment due to uniform temperature change is negligible here because it is not differential temperature scenario. we had differential temperature formula. But in this case, since uniform temperature change, we have only focus on this thrust. So that is not required because of this uniformity of the temperature changes. If it is differential, we are going to find out, the formula. According to that, we are find out the movement due to the temperature. So like this, we are understanding these kind of scenarios in this. These are some of the web references which we are going to understand for these particular secondary stresses which are in these two hinged arches. Thank you. We will see in our next class.
Like, share and subscribe. Hit the bell icon for more updates.